Did you know that Pink Floyd were scientists themselves? Well, not really, but they did get one thing right on their album cover for The Dark Side of the Moon. Here you see a very common phenomenon of white light being split into all its component colors, the rainbow, when it hits a prism. Well, all those components of colors are nothing but the visible light spectrum that we know of today. What Pink Floyd forgot to mention on their album was that atoms themselves can produce their own unique colors as well. Here's an example of a sample of hydrogen that's placed inside of a discharge lamp. When electrons are shot at the sample of hydrogen, the hydrogen produces a purplish kind of tinge in color. Now, if we break down that purple tinge into all its separate components, we'll see that hydrogen actually emits photons of the red, blue, and purple wavelengths. And scientists are able to quantify this and give it its own unique emission spectrum. Now, electrons can be shot at any atom in a discharge chamber. However, only hydrogen will emit these specific types of wavelengths of light whenever electrons are shot at it. Hence, you can kind of think of this as a unique fingerprint for every element on the periodic table. This unique element is called the atomic spectra. Scientists did note that if you shot electrons at atoms, you were able to produce colors. However, what they didn't know was why that was possible. Now, nobody knew until Niels Bohr came along with the Bohr model of the atom. The Bohr model was an interpretation of how atoms were organized, with the nucleus in the center containing protons and neutrons. At any given time in the Bohr model, electrons are orbiting around the nucleus in what are called energy levels, these concentric circles that I've drawn here. I've only drawn the first two energy levels of an atom. However, according to the Bohr model, there are multiple energy levels. Here, I've only depicted the first two for the hydrogen atom. As you may recall in the previous video, light contains little packets of energy called photons. When a photon hits an electron at just the right amount of energy, the electron will actually jump from the bottom energy level to the topmost energy level, like that. This jump in energy from the first energy level, so let's call that n equals 1, to the second energy level, and let's call that energy n equals 2, this jump in energy between n equals 1 to n equals 2 is a very, very specific amount of energy, and that is called a quanta. Now, if the photon had been just even a little bit more energetic or had just a little bit less energy, this electron here would not have made the jump from n equals 1 to n equals 2. It's very important to realize that a photon must correspond to the exact quanta difference between the n equals 2 energy level and the first energy level. It can't be anywhere in between. Now, it might be easier to think of energy levels kind of like a ladder. So let's just draw a ladder here. There's one rung, there's a second rung, there's a third rung. So if you're climbing the ladder, you need to take one foot and place it on the next rung. However, you can't take one foot and place it in the middle of a rung. There's going to be no place left for your foot. So it's easiest to think of your electrons kind of like your feet. Your electrons can only jump between certain rungs of a ladder, but they can't jump in between rungs of a ladder. Alright, so now let's go back to our example here. So let me just clean everything up here. We have an electron that's in the second level of energy. And so what it'll do is it'll keep going around in the second energy level and just keep orbiting around the nucleus. Now, it has a higher amount of energy in it than it did when it was at its previous state on the first level of energy. However, the electron won't be rotating or orbiting around the nucleus at this higher energy level forever. All things want to come down to a lower energy level. So what's going to happen is the electron itself is going to emit some energy in the form of a photon. So let's grab this photon here. So it's going to emit the exact same amount of energy in the form of a photon, And what will happen is it will demote itself back down to the first energy level, back to where it used to be. And this photon will go about its merry way, and it will have its own certain wavelength of light because it has a certain amount of energy to it. And that wavelength of light is what we see whenever we hit the hydrogen atom with electrons in the discharge chamber. Now, let's go back to our early example here with the hydrogen emission spectrum. So what we saw earlier was when photons of certain wavelengths hit the electrons at a precise energy value, aka the quanta. When those quantas were satisfied, the electron here, in this example, would jump up the rungs and would travel up above into higher energy levels. And eventually, it would descend back down to the baseline, but the only way it would descend back down was if it emitted something like a photon of a specific color. So let's look at a specific example here. Let's say we shoot a red colored photon at the hydrogen electron here. What's going to happen? Well, the electron itself is going to jump up into a certain energy level. So let's correspond that with this quanta of energy. After a certain amount of time, the electron is going to get kind of bored, and it's going to say, well, I want to come back down to my baseline. And so how does it come back down to the baseline? Well, the only way it comes back down into the baseline is by emitting an equivalent quanta of energy. And the only way it emits that quanta of energy is through a red photon, similar to the red photon that excited it in the first place. So now, let's consider another example. Let's say a yellow colored light, a yellow colored photon hits the hydrogen electron here. Now keep in mind, in the hydrogen emission spectrum, we don't see any yellow colored lines. So, if a yellow colored line hits the electron here, nothing's going to happen because the electron doesn't have the right quanta of energy to jump in between into some miscellaneous rung in between n equals 2 or n equals 3. That's not possible according to the Bohr model. So what's going to happen is the photon of light is going to just pass through the electron and just continue on its merry way. The electron won't be excited, it won't go down anymore, it'll just stay at baseline and it'll just keep orbiting around the nucleus. Likewise, let's say if we have a green colored photon which is not on the emission spectrum, nothing will happen. The green colored photon may have enough energy to send the electron into this certain energy level. However, that doesn't follow the rules of quantized energy, and so therefore this is not allowed. What will happen though is the green photon will just pass through the electron and nothing will happen. The electron is happy to stay at baseline because it doesn't have the exact amount of energy it needs to jump into a new energy level.